Welcome to this unit on the process reaction and the black box model. We have introduced to you the theoretical product reaction for cell growth. Substrate plus nitrogen source plus zero oxygen goes to cells, CO2, water and protons, where the coefficients follow from conservation principles for elements and electrical charge. Please note that CO2 and water are not always products, they also can be substrates. See for example the reactions with methane or carbon monoxide, where 0.525 methane plus 4.475 CO2 and 0.2 ammonia go to 1 biomass, 0.45 water and 0.2 protons. And for carbon monoxide you can see the reaction, it requires water and produces CO2. If not cells, but an organic compound is produced, then the theoretical product reaction follows accordingly. For example, for 1,3-propanediol PDO from glucose, 2/3 of glucose plus 0 ammonia goes to 1 propanediol, 1 CO2, 0 water and 0 protons. This shows that the minimum glucose requirement is 2/3 mole glucose per mole PDO. A useful step is then to find out if Gibbs free energy is produced or consumed in this reaction. The Gibbs free energy change can be either negative or positive. If it is negative, free energy is released and it is possible to run the reaction under anaerobic conditions. This often applies to producing small molecules such as lactic acid or ethanol, but also for the PDO reaction, in which about 110 kJ per mole Gibbs energy is released. Thus, we can distinguish two product classes. It is a big advantage if the process can be run without oxygen, because the operation will be a lot simpler, without mass transfer and cooling challenges. For larger, more complex molecules, as a rule of thumb, the Gibbs energy change is positive, and oxygen is required to combust the substrate, the catabolic reaction, and run the process. It is now time to introduce an important tool for design and evaluation of bioreaction systems, the process reaction. Substrate plus oxygen plus nitrogen source goes to cells, product, CO2, water and protons, and heat is formed and Gibbs energy is released. When normalized to 1 mole product, the coefficients in this equation are ratios of Q rates. But first, let us ask ourselves what determines the Q rates. Every practitioner will understand that this is mostly governed by the pressure, pH, temperature and concentrations, or only concentrations when keeping the physical environment constant. This could present complex kinetics for Qi. Is information on the metabolism important? At this stage, no. We can work with the cells as a black box. We do not have to know details from the inner metabolism of the cells. This is due to the basic concept of the limiting substrate, a kind of magical trick. In the process, there will always be one key substrate that is limiting. For example, the glucose, ammonia or oxygen. And that results in an upper level of Qs, Qn or Qo. All the other compounds are in excess. This can be understood in terms of the transport of the limiting compound into the cell, which is governed by enzyme or transport kinetics. The Q rate is then a hyperbolic or saturation type of function of the limiting substrate concentration. We can now define two uptake regimes, excess and limiting, distinguished by the ratio of Cs over Ks. Excess is happening when C is larger than 20 times K, and limiting when C is below 20 times K. In the excess regime, Qs equals Qs max, while in the limitation regime, the Qs rate only depends on Cs. Inside the cell, all the fluxes of the metabolic pathways can then be assumed to be in synchrony. This is called flux coupling, where all intercellular concentrations are in steady state and all Qi rates depend only on Qs. This will allow the black box simplification. The next step is to understand energy consumption and production. A cell always requires energy for maintenance purposes, to keep membrane gradients intact, for repair of damage and to cope with stresses. The substrate catabolism is then a result of three mechanisms. Substrate goes to cells, product or maintenance. This results in the Herbert-Pert substrate distribution relationship, and in this form applies to products that are consuming energy. Then we need an aerobic process and rely on kinetic coupling of Qp and mu. This is usually a non-linear relationship between Qp and mu. The black box model has three relations: glucose uptake, Herbert-Pert and Qp mu, with four variables: Cs, Qp, Qs and mu, and this gives only one free variable for which often Qs or Cs is taken, and it can also be mu. Let's apply this to our model system on 1,3-propanediol PDO. Also here there are three equations with four variables and one free variable which can be Cs, mu or Qs. We want to know the optimal mu for which is the ratio Qs over Qp minimal, or what are the minimum substrate variable costs to make the product. Derivation of the following relationship for this ratio Qp over Qs is then 1.05 plus 5 times mu plus 0.003 divided by mu. Then the optimal conditions calculated by taking the derivative of this equation are at mu 0.00245 per hour, and at this mu about 25% of the glucose goes to growth, 62% to product and 17% to maintenance. Now, I understand that this may not be easy to follow, but for more details I refer you to a separate MOOC on industrial fermentation as developed at the Technical University in Delft and available under the same platform as this MOOC. If small molecules are made and sufficient Gibbs-free energy is released in the product reaction, then an anaerobic process is possible. And this is called stoichiometric or energy coupling. Substrate flows into maintenance and growth. Qs is a constant multiplied by mu plus the maintenance coefficient. And product is formed linearly proportional to mu. Qp is a constant multiplied by mu plus the maintenance for product formation. The energy required for the substrate uptake and growth is completely provided by the formation of product. And as a result, we have two independent equations, glucose uptake and Herbert-Pert, and three variables, Cs, Qs and mu. It is thus simpler than the aerobic case. In the next unit, we will dive deeper into the example of producing PDO from glucose, understand parameter identification needs, derive and evaluate the process reaction, and suggest ways to improve sustainability.